everyone, welcome back to Python for Bioengineers. Today we're going to be talking about Tellurium, what it is, and how to use it. So Tellurium is a Python package that allows for easy modeling and simulations, and Tellurium is useful for any system that can be represented by ODEs, but it's especially useful for simulations of biochemical reactions. So Tellurium can be used in Spider, which is a part of Anaconda Navigator. And for this video today, we will be assuming that you already have Tellurium installed on your device using pip, which if you have not done that, you can go watch our tutorials on using pip install for either Windows or Mac. So the first thing that we'll do in our code is actually importing the Tellurium package, which will be using the shorter name TE4, and that is in this line of code here. It isn't required to use this shorter name TE, but it's pretty standard practice. It makes you not have to type as much later on in the code. And then next, we will be writing something called an antimony string, which is this part here. And an antimony string is a human-readable way of writing out a system. So when we call tellurium.loadA here, this loads in the model from the antimony string and stores it in a variable R. And while it's not required to call this variable R, it's pretty standard practice, and because this variable is of type Roadrunner instance, which is the program that's used to solve the system, but you likely don't have to understand much about Roadrunner. Just know that you'll be writing out R equals tellurium.loadA. So going into what's actually contained in this antimony string here, inside the antimony string, we first write out the reactions that are occurring. So in this example, we have a system with 3 reactions and their associated kinetics. So writing the J1 through J3 labeling is labeling the reaction numbers and the associated rates for the reactions. So for example, the first reaction is A becomes B at a rate of K1 times the concentration of A, which we'll be defining both of these values later on in the antimony string. So one thing that's important to note is the formatting of writing an arrow with a hyphen and then a greater than sign to represent the reaction, as well as that for each of these reactions, we define the rate right after as well. So the next part of the antimony string is that we'll be defining the concentration/amounts of each species as here. And then we'll also be defining the reaction constants K1 through K3 that we were using up here. So one important thing to note is that if we didn't include one of the species concentrations, it's assumed to have an initial concentration or amount of 0. So for example, if we commented out A, it would be assumed that A was set to 0, or if we just didn't have A at all, it would also be assumed that at time 0, A would be set to 0. So going back to what we originally had, and then moving on to actually simulating this system of equations. In order to create a time course simulation of our model, we'll be calling r.simulate, where R is the Roadrunner instance that we just created up above. And then the 3 parameters being passed in here are the start time 0 in this case, the end time 10 in this case, and then the number of points being simulated, which is 100 in this case. So make sure that you have enough time points in this variable here that you can see a smooth curve of your reaction rather than having discrete or straight lines in the simulation plot. But you also don't want to have too many points that you're performing an extreme amount of computations. So I'd say a pretty safe number of points to start out with is 100, and you can play around with this number and also the end time until you find an appropriate time frame for your system. Also, in this example, I'm saving the simulation to a value called result. That's the result equals part. It isn't actually necessary to save this value, but I'll be showing you how to save it in order to work with the results later, which you can see here from a previous simulation. This is what the saved results will look like. But for the purposes of what we're doing today with just creating a plot, technically you could just say r.simulate and not actually save this. And then in terms of actually plotting, we'll be calling just r.plot with no parameters passed in, and this will create a time course plot with the species labeled. So I'll hit the run button up here to see what our antimony string produces. And this is the result. You can see that each of the species is labeled. It goes from time 0 to time 10, like we indicated. And you can see that it just happens that with this system, it looks like they appear to go to steady state. So in conclusion, this is just an intro to the basics of how Tellurium can be used. But the package Tellurium is really useful and it's very well documented online. So you can go to the documentation to find many more examples of the methods that you are planning to use and explore even more. Thanks for watching.